Hello everybody, I hope you're all doing well, staying safe. So today we're going to solve a problem on rigid body kinematics, and in this particular problem we will make use of the idea of the instantaneous center of rotation for the velocity analysis. Okay, so here is a problem. I've drawn the problem here. So at this instant in time, the bar DBC, or the bar CD if you want to think of it this way, so at this instant in time, okay, the bar CD is vertical, and the bar OA is horizontal. Okay, and you're told that the angular velocity of the bar AB, where B is a point on the bar CD as well. Okay, so let me write that down. So B is a point on the bar CD. Okay, and let me write my D carefully. It looks like an O. All right, so at that instant in time, you're told the angular velocity is so many radians per second, and you're told that it remains constant throughout motion. Okay, angular velocity of link AB is constant at 40 radians per second throughout motion. Okay, so that's the information that's given to us, and what do we need to find in this problem? Okay, so this is given, and to find, we need to employ the velocity analysis to find the angular velocity, the Icr analysis. Okay, so find, okay, so using the instantaneous center of rotation method, obtain omega OA and omega CD. Okay, so that's two things that we need to find out. And then once we do this, we can find out the accelerations using acceleration analysis. Using acceleration analysis, obtain alpha OA and alpha CD. Okay, so those are the two things that we need to obtain. Okay, so this is alpha OA. All right, now once again, let's very quickly go back and look at the problem. I have this bar CD, which is vertical. I have the bar OA, which is horizontal. Point C and point O are fixed points. Okay, so C and O, these are fixed points, which means that their velocities and accelerations are going to be zero. Omega AB is told to you to be a constant angular velocity, which means that alpha AB is going to be zero as well. And I need to employ the Icr method to find the angular velocity of CD and OA, and I need to employ irregular acceleration analysis to find the angular acceleration. All right, so I'm going to grab this figure and bring it down here with all the dimensions included. Okay, and let's write down whatever information is given to us in the form of the vector quantities. Okay, so here I'm going to do a couple of things. I'm going to first of all assume that the angular velocity of OA and CD are counterclockwise. Okay, so I'm going to assume the following. Okay, I'm going to assume that the angular velocity and angular accelerations are in the following manner for each of them. Okay, this is typically what we do whenever we solve a problem, right? So this is going to be omega of CD, and then this is going to be alpha of CD. This is going to be omega of OA, and then this is going to be alpha of OA. Okay, and based on this, I will also assume some kind of a fixed reference frame, IJK coordinate system. Okay, and I can draw it anywhere. Usually you would like to draw it at a fixed point, so you can draw it at the point O if that is the case. I'll just draw it on the side here, okay, so that this doesn't clutter our figure as much. Okay, so here is the I coordinate and J coordinate system. And in this problem, I'm okay to just go away with the IJK, because at this instant in time, these links are all horizontal and vertical. Okay, so, and for any problem, I can always solve it using the IJK coordinate frame. The only thing you got to keep in mind is that this is a fixed frame of reference. Okay, so this is a fixed frame of reference. Fixed frame, it can be either fixed outside the body at a fixed point, or on the body I can fix it at point O or point C, which are both fixed points. Okay, all right, things that I know in this problem. So I'm going to assume the following, and we are assuming that the angular velocities, so let me also do one more thing here. I had to underline this using the color scheme that was following. Okay, so here I'm assuming omega OA is omega OA in the K, then alpha OA is alpha OA K, omega CD is omega CD in the K direction, and then alpha CD is alpha CD in the K direction. Okay, and then information that is given to me, I know that omega AB, omega AB, I'm told is counterclockwise, as you can see from the curl of the arrow. Okay, so this is going to be 40 K radians per second. Alpha AB is 0 radians per second, because omega AB is a constant. Because omega AB is constant. And information that can be discerned from the problem is that the velocity of C is 0, acceleration of C is 0, velocity of O is 0, and the acceleration of O is 0, because these are fixed points. Okay, so this is the situation that I have so far. And of course I have all this dimensions and so on. So how do I perform the velocity analysis? So let us perform the velocity analysis. Using the Icr method. Okay, so here is what I do. Now, I go back to my figure. I look at each and every one of these bars. Okay, so I'm going to grab this particular bar here. So I'm going to grab the bar CBD. So I'm going to copy that, and I'm going to bring that down here. Okay, then I know that the point B was sitting somewhere here, if I remember right. Okay, so that's where the point B was sitting. So let's label that. So this is point D, this is the point B. Okay, now from common sense, we can see that since the point C is a fixed point, this entire bar has to be rotating about the point C, which means that at any instant in time, the path of the point B is going to be a circular path. Okay, so if I draw that circular path right down here, okay, so let me draw something that is approximately circular. Okay, and let me draw it in a shaded manner. Okay, so I'm going to shade this here. Based on the direction of the angular velocity omega CD, I know that the direction of the velocity of B is going to be pointing this way. Okay, so I know that this is going to be the direction of the velocity of B. I hope you agree with me. Okay, and so what I'm doing here is this. Okay, so since I'm going to write this down, so since C is a fixed point, the point B on bar CD will travel along a circular path of radius 0.15 meters. I think if I bring my dimensions, let me bring my dimensions as well. Okay, just so that it is a little more convenient for us to have it out here. Okay, so if you want, these are the dimensions, and this is the point D. Okay, I guess my dimensions are kind of crowding the figure, so hang on a minute, let me write it out nicely. I think I should be able to get away with this. Or yes, that is not bad. Okay, all right. Apologies. Okay, so since C is a fixed point, let's maybe write this properly. Okay, so since C is a fixed point, the point B is going to travel along a circular path of radius 0.15 meters. About point C, and this is true of any other point on the body as well. Of course, the radius is going to be different, but for example, if I look at point D, that point is going to travel along a circular path of radius 0.15 plus 0.075. Okay, all right. So this implies that based on the direction of omega CD, we can see that velocity of B will be horizontal and pointing left. Now, is this correct? I don't know. Okay. Now, is the direction left or right? Okay, so we do not know the actual direction of VB, that is left or right, but we do know that it's going to be horizontal. But we do know that VB is horizontal at that instant in time. Okay, so that's something that we can see. So I just want to underline something here. So VB will be horizontal. Okay, that's something that you want to notice. And based upon the direction of omega CD, VB will either be pointing to the left or to the right. Now, does it matter to me? Not really. Okay, as you'll see in the instantaneous center of rotation method, perhaps my angular velocity is not in the direction that is shown. If it is, then well and good. But if it is not, then I just have to change it to the other direction without telling anybody. Okay, all right. So now what do? I do the same thing for the bar OA. Okay, so this is I look at bar CD. So look at bar CD. Okay, so this is the first step in our analysis. Okay, then the next step is I'm going to look at the bar OA and do the same thing. Okay, so let's see. Look at the bar OA, and of course when you do the actual problem, right, you'll see that this is going to be much faster than what I'm doing here. Typically, as I'm solving a problem, I'm writing it out and then explaining it to you, so it takes a little longer. Okay, but if I were to sit down and just do this problem by myself, this problem would probably not take any more than 10 minutes. Okay, typically it should not. Okay, all right. So if I now go and look at the bar OA, okay, so I'm going to grab that bar here. Okay, let me grab the bar OA, so copy that, and let me bring that down here. I guess I don't need this guy. Let me just have a dimension right through here. Okay, Hopefully that's a straight line. Most of the times I struggle to draw straight lines. I draw straight lines better on a chalkboard, I believe it or not. Okay. All right. So here is my dimension. Here is the point A, which is sitting at the end of this bar here. So if you want, you can put in the knob that was present there, or the pin that was present there. Now, once again, you can see that the direction of the velocity of A, because point O is a fixed point, velocity of A is point A is going to perform a circular, is going to travel along a circular path, okay, around the point O. Okay, so if I draw a circular path here, okay, so this is approximately circular. Okay, so and if this is the case, then I know that the velocity of A is going to be in the vertical direction. Okay, so this implies that for me the velocity of A is going to be tangent to that particular path, and it's going to be in the vertical direction. And the idea is, okay, why is it pointing up? This is because of my choice of omega OA. Okay, because omega OA is trying to rotate the bar such that the point A is going to travel vertically up at that instant in time. Okay, so let's write these things down as well. Okay, similar to what we had written for the previous bar. Okay, so since O is fixed, okay, the point A is going to perform, so point A is going to rotate about O along a circular path. Along a circular path. Okay, so this implies that based on the chosen direction of omega OA, we can see that VA is going to be vertical and upwards. Okay, now the question is, does it matter if it is upwards or downwards? I don't know. Okay, so we are not sure if VA is up or down because we don't know omega OA. But we are sure, I just want to write this omega OA better. Okay, looks like my eraser has grown in size. Okay, but we are sure that VA is vertical at that instant. Okay, these are all taking place at that instant in time. Okay, so we are now sure that the velocity of A is vertical. Okay, so this is all the information that we can draw from the velocity of A. All right, now I bring the bar AB. Okay, this is where the things are going to be happening. Okay, so if I bring the bar AB, so let's grab that creature. My hope is I can grab those things as well. So let me see. So now let us look at the bar AB. Okay, so this is what we are coming to. This is where the ICR is actually going to be used, because this is where I know some information regarding the angular velocity of the bar. Okay, so if that is the case, then let me bring this bar. Okay, so I have some information here which I don't need that guy. All right, this is fantastic. Now I know that the direction of the velocity of point B, so point B was sitting here, right? I know the direction of its velocity is pointing to the left, right? How do I know this? This I know from this figure here. So I'm going to grab that guy and come. Okay, so maybe with the path as well. So I'm going to copy that. and I'm going to bring that down here. Okay, so this I know is the direction of the velocity of B. Velocity of A I know from the path that is being followed from here. If I copy that and if I bring it down here, okay, so this is going to be the path of the point A, and it's going to be pointing vertically up. Now, instantaneous center of rotation, so here is where I use the Icr method. Okay, so can use the Icr to obtain velocity of A and the velocity of B, since we have the angular velocity omega AB and direction of the velocities, direction of VA and VB. Okay, so that's why I can use the Icr method here. And now watch this. An instantaneous center of rotation always lies along a line that is perpendicular to the velocity, which means that it's going to be lying along a line that is perpendicular to the velocity of A. Okay, so there is one line here. Well, that doesn't look perpendicular, but hang on a second. All right, beautiful. So this is going to be perpendicular to that line, right? Then I'm going to have the velocity of B pointing to the left, which means that the instantaneous center is going to be lying perpendicular to that line as well. Okay, so this is going to be a line where the instantaneous center is lying along, which means that the instantaneous center is going to be actually at the intersection of these 2 points. Okay, so the actual Icr is going to be at the intersection of these 2 points. Okay, so this is the instantaneous center of rotation. Okay, this is the Icr, and what do you know, if I actually bring back my original figure, so this is the Icr, so I need to know the distance, right, between point B and the Icr. So let me label this distance as R. Well, I need to, so R B to Icr, and then this distance is RA to Icr. And before I go ahead and do the distances and so on, something that I can easily write using the right hand rule, I know that the magnitude of VA is omega AB times RA Icr. Okay, so magnitude of VA is omega AB times RA slash Icr. I know that the magnitude of VB is going to be omega AB times RB slash Icr. Is my direction of VA and VB correct? Okay, if I use the right hand rule, if I assume that this is the direction of VA, then if I use the right hand rule and place the fingers of my right hand aligned with the velocity VA and my palm is facing the Icr, if I curl my fingers, I get a counterclockwise rotation. Likewise, if I do the same thing at VB, I get a counterclockwise rotation. I know that omega AB is counterclockwise, so the directions assumed are correct. Okay, so is the direction of VA and VB correct? Okay, so here is what we do. Align the fingers. So we know the direction of omega AB. We know omega AB is counterclockwise. Okay, then align fingers of right hand with VA and VB respectively separately. So VA and VB separately. Right, this is, you're going to be doing this 2 times, one for VA, once for VA, and once for VB. Once for VA and once for VB. Okay, then your palm, when you're doing this, should face the Icr. Okay, then curl your fingers. What is the direction of your thumb? Thumb direction is the same as the direction of omega AB, which was given to us as counterclockwise, which means that, okay, This way I see that the direction of VA and VB is correct. Okay, hence, since VA and VB both give a omega AB that is counterclockwise in sense, which goes with the info given at the problem. In the problem, this implies that the direction of VA and VB is correct, okay, as we assumed. Okay, so hence we assumed the correct directions for VA and VB. Okay, so that's great news. Okay, so once again, it's a lot of writing, but I just want to make myself very clear here. My question is, okay, how did I find the ICR? ICR is along a line perpendicular to the velocity of any point on the rigid body. So velocity of A is pointing vertically up, so ICR has to be perpendicular to that velocity. Velocity of B is pointing to the left, so ICR has to be perpendicular to that velocity, along a line perpendicular to that velocity, which means that at the point of intersection of these two lines is where the ICR is going to be. Okay. Now, is the direction of VA and VB correct? Are they pointing up or down, or are they pointing left or right? Use the right hand rule. I know that omega AB is counterclockwise. Okay, so this is given to me. This is given to me as 40 radians per second and counterclockwise. Then if I use the right hand rule for VA, fingers of my right hand aligned with VA, my palm faces the ICR. I curl my fingers, I get the thumb pointing outwards, which tells me that the direction of omega AB, because of how I assumed VA, is also counterclockwise. Then the direction of VA is correct. Likewise, I do the same thing for VB. It assures me that the direction of VB that I have is also correct, because the sense of omega AB I get using the direction of VB I have assumed is counterclockwise. And this is using the right hand rule. Okay, so this is what we have found out so far. Now I'm going to grab all of this information and I'm going to make it to work. Okay, so I'm going to copy this here. And so there are three things that we have so far. So here is one. Okay, then I'm going to grab the other two bars as well that we have worked hard on. So here is one of them. Okay, so I'm going to copy that and bring that down here. Okay, and you can automatically see, so let me bring it down here. Okay, you can automatically see from this bar here that VB is going to be the distance from RBC multiplied by omega CD, right? If I use the general equations. So here I know from basic analysis that VB is going to be omega CD times R B slash C. This is just the magnitude. Okay, so these are all magnitudes. Okay, so this is also magnitude. And then I also have one more thing that I can grab from up here, which is this bar that we were working on. And likewise, you can also see that the direction of VA is pointing up, and the value of VA can be easily given to us as well. Okay, so from here I can also say that VA is going to be omega OA times the length. Okay, so this is going to be omega OA times the length from O to A, which is RA slash O. Okay, this is once again the magnitude. Okay, the only thing I need to do is locate where the ICR is actually physically, and that's fairly straightforward. The intersection of point B and point A, and because the ICR is along the line horizontal, it has to be the point C itself. Okay, so maybe if I make use of my original figure here, okay, so if I take my original figure here, I'm just going to grab only that. well, with the dimensions, of course, I guess, right? I'm going to grab all of that. So far I have not used any vector analysis, as you can see, right? So if I bring my actual figure here, I can automatically see that I need to maybe draw some thicker lines here, but I can automatically see that since the velocity of A was pointing up this way, okay, so this was the direction of velocity of A, the velocity of B was pointing this way onto the left. Okay, so this was the direction of velocity of B. The ICR has to be along the line that is perpendicular to the two, right? So here is one line, and then here is the other line, and the intersection of these two is actually the point C, which means point C is the ICR for me. Okay, so point C, as you can see here, is the ICR for bar AB. Okay, so that is an important thing. It is not an ICR for other things, it is an ICR for bar AB. It is a fixed point for the bar CD. Okay, and point O is a fixed point for the bar OA. Okay, so this is the ICR for just the bar AB. Okay, not for anything else. Okay, so this is for the bar AB. Okay, so which means that if I now collect all my information from here, okay, so I have all of these things which I can bring forth. I'm just going to bring them out here. Okay, so that's one thing that I have. Then I have omega CD related this way to VB. I can write it right next to it, and I can also write this creature right next to what I have. Okay, and then I can obviously also see that my distances are known to me. So RAO is 0.1 meters. These are all magnitudes. You see, I'm not putting any vectors on top. Okay, then I'm going to have R B slash C. Okay, this is going to be 0.15 meters. And then C is the ICR for bar AB. So which means that R B slash ICR is going to be the same as RB slash C, and then RA slash ICR, this is of course 0.15 meters, and RA slash ICR is the distance from point C to point A, which is going to be RA slash C, which is going to be 0.1 plus 0.1 or 0.2 meters. Okay, I hope this is obvious to everybody here. All right. Once I have everything done, then all I have to do is just bring it all together. Okay, so from these two equations, let me underline them here. Okay, so from these two, it is very obvious to see that I can equate those two velocities together. Okay, so which tells me that omega AB times RA ICR is equal to omega OA times R A slash O, which implies omega OA is going to be omega AB times R A slash ICR divided by A slash O. And the direction of omega OA is correct because the direction of VA is pointing upwards. Okay, so that's something that we can also make a note of. So angular velocity omega OA is actually correct, direction of VA is correct. Okay, so we put this in the correct direction. Okay, so this is the correct direction, and since the direction of VA is pointing up, omega OA has to be counterclockwise. Okay, so this implies that omega OA is omega OAK. Okay, so it is counterclockwise. Okay, likewise the direction of VB is correct. Okay, so this is the correct. Who said this was the correct direction? We just did that from the Icr analysis. Okay, and so this implies that omega CD has to be, my C, my O and D look the same. I'm pretty mad at that. So this is omega CD times K. This is also counterclockwise, so this direction is correct, and likewise the direction of omega OA is also correct. Okay, So if I go back now to my actual calculations, I can calculate the magnitude, substitute for all of these, and I end up getting omega OA to be the following value. It's around 80k or 80 radians per second, the magnitude, which implies that omega OA is 80k radians per second. Okay, and then likewise I can do the same thing. I can say that omega AB or B slash ICR is equal to omega CD times or B slash C, or omega CD is omega AB or B slash ICR, all of this divided by R B slash C. Okay, R B slash ICR and B slash C are the same actually, right? Which implies that omega CD is 40 radians per second, or omega CD is 40k radians per second. Okay, so we are done with the velocity analysis. Okay, so this is the end of the velocity analysis. I'm going to look at the acceleration analysis. All right. And in the acceleration analysis, we are just going to use the generic equations. Okay, so we use the generic equations. I needed that line. I'm not sure why that vanished, but anyways, so we use the generic acceleration equations. Okay, now what do I typically do in this situation is I bring in all the respective bars that we have, okay, and then I write out the acceleration expressions. Okay, so let's start with the bar CD. Okay, so start with bar CD. Okay, I'm not interested in the what is my strategy? My strategy is the following. Okay, let's take a look at strategy. Okay, so point B is a point on the bar CD, point B is a point on the bar AB, so I can relate the velocity or acceleration of point B on both these bars together. And since I already know omega OA, I can also write the angular acceleration of OA in terms of the point A. Okay, so that's my point of view here. Point B is a point on two bodies, point A is a point on two bodies. I'm just going to relate them to each other. Okay, and then I'm going to relate point B to point A as well. Okay, so here is the situation. So let me bring each of these things down here. Okay, I don't want to grab that. I would rather grab the cleaner figure from here. Okay, so I'm going to get this and bring it down. Okay, so I have the bar CD, which is right down here. I don't need the velocity and so on because I've already taken care of all of that. Okay, so the only useful thing that I'm going to get from here is we already know the following. So we know that omega CD is 40 radians per second, and I know that the acceleration of C is 0, and then C and B on the same body, okay, which implies that the velocity of B slash C relative is 0, and then the acceleration of B slash C relative is also 0. Okay, so I'm going to relate the velocity acceleration of B to the acceleration of C. Watch this. So acceleration of B is acceleration of C alpha CD crossed with R B slash C, and minus omega square CD, the scalar, R B slash C. Then I'm going to have A B slash C relative, which will be gone, 2 omega CD cross V B slash C relative. Okay, I'm going to get rid of many quantities. AC is gone, then this creature is gone, then this creature is gone. Okay, so if I do the substitutions, I end up getting the following. Okay, so AB and I had assumed alpha CD to be counterclockwise, as you can see here, right? And then RBC is easy to write. RB/C is going to be sitting from point 1,5, and this is pointing in the direction of the J unit vector. Maybe it's a good idea to bring in the unit vector system as well somewhere here. Let's see. Let me draw that right out here. Okay, so here is my I, J, and K coordinate frame. This is I, this is J, and this is K. Okay, so RBC is going to be 0.15 in the J direction. Okay, sitting at the point C and looking at the point B. Okay, so this is the typical situation, and if you want, you can draw this out separately here. So sitting at the point C, looking at the point B. Okay, so this is going to be our B/C. Okay, so alpha CDK crossed with 0.15 in the J direction, and then I'm going to have omega square CD, which is 40 square times 0.15 in the J direction. Okay, and K cross J, if you can write the triad here, so this is I, this is J, this is K. Okay, if I do this here, K cross J is minus I, which tells me that acceleration of B is going to be minus 0.15 alpha CD I, and minus 40 square times 0.15 times J, so many meters per second square. So let me put a line underneath this. Okay, so because we're going to start collecting all of these things, and we're almost there. Then let me grab the next easy bar. Okay, let me go to bar OA. Okay, all right, so this is what we had so far, bar OA. If I go up and bring the cleaner looking figure from here, okay, and you see this is nothing but the same vector equations that you had been using in the past. Okay, so there is not much of a difference in these things. Okay, so I'm going to cut off that. So this, obviously we know some information about this bar, point O and A on the same body, which implies that acceleration of A/O relative is 0, velocity of A/O relative is 0. Okay, and then CO is a fixed point, which implies that acceleration of O is 0. And we found out that omega OA was 80 radians per second. Okay, this was from the Icr analysis. Okay, then I'm going to write the acceleration of A is acceleration of O, alpha OA crossed with RA/O, omega square OA times RA/O, A/O relative, and then 2 omega OA crossed with VA/O relative. Okay, so that's what we have so far. Get rid of these terms. This guy is gone, this guy is gone, that guy is gone. Write it out. Acceleration of A is alpha OA in the K direction as assumed, RA/O. Okay, this is fairly straightforward, right? I'm sitting at the point O, and I'm looking at the point A. Okay, so this is going to be RA/O, and you obviously know this is in the I direction, so this is crossed with 0.1 I. Okay, and then this is going to be 80 square times 0.1 I. Then you can write down your triad from above. Just going to grab that guy. Okay, and based upon the triad, acceleration of A is K cross I is J. Okay, so that's 0.1, or let me write it down this way. So this is going to be 80 squared times 0.1 I plus 0.1 alpha OA in the J direction. Okay, so that's what I have. All right, so we're almost done. Okay, now all we have to do is write the acceleration of A, relating it to the acceleration of B by looking at the bar AB. Okay, so that's the third step. Okay, so bar AB is where I'm going to be focusing my attention on, and let me grab that bar from here, somewhere here, I guess. All right, wherever I see just the ice here, but let me maybe bring out this main figure here. Okay, so that's something that we can anyway make use of, right? So I'm going to copy that. Excuse me. And I'm going to bring that down here. I'm going to clean up some of these things. Okay, so I don't need any of that. I know velocity omega AB, I know that. I don't need any of those things because I'm looking at just the bar AB. Okay, I'm going to cut that off and cut that off as well. Okay, and I guess I don't even need this. Well, let me just keep that there. Okay, doesn't do any harm for me. Okay, so far so good. I can cut that off and cut that off as well. All right, so beautiful. Point A and point B are on the same body. Okay, which implies that acceleration of let's say B slash A, it doesn't matter, you can call it as A slash B as well. Acceleration of B slash A relative is equal to 0. Velocity of B slash A relative is also equal to 0. Then I know that omega AB is 40 radians per second, and omega AB is constant, which is given, which implies that alpha AB is 0. Okay, then I start relating the acceleration of B to acceleration of A. Acceleration of B is acceleration of A. This is going to be alpha AB crossed with R B slash A, omega square AB times R B slash A, then B slash A relatives who are not invited, then AB crossed with V B slash A relative. Get rid of many of these things. Alpha is gone, AB relative is gone, this is also gone. Okay, and then how do I write A B slash A? Okay, so that's quickly done here. Okay, so if I look at it this way, this is the point B, this is the point A, this is the vector B slash A, which means I travel to the right, travel to the left, and then I travel vertically up. Okay, I travel to the left by how much of a distance? If I go from A to B, that's going to be 0.1 meters plus 0.1 meters, so that's 0.2 meters, I'm sorry. And then going from A to B vertically up is 0.15 meters. So this tells me that R B slash A is going to be minus 0.2I 0.15 J, so many meters. Okay, take this and substitute this back. So this tells me that acceleration of B is acceleration of A minus omega square AB, so that is going to be 40 square times minus 0.2I 0.15 J. Okay, so this is what I have. But I already have an expression for acceleration of B and A, which I'm going to grab from up there. Okay, so this is what I have from the bar AB. Okay, so far what we have. So we have the following. Okay, so this is first of all from the bar AB. Okay, that is not intended. I'm going to paste that here. Okay, so this is from the bar AB. Okay, then I'm going to grab the other two as well. Okay, so this was from the bar OA, so copy that. Okay, so this was from the bar OA, and then I also had from the bar CD. There was that creature lurking somewhere here, that is this guy here. Okay, so copy that, and of course all of these are in meters per second square. If you want, you can write the dimensions right down here, meters per second square. Okay, and the last one, which you can write down here. Okay, so this was obtained from the bar CD, okay, of which B was a point. And you obviously see what the next step is, right? I can take the expression for A and then substitute it directly on there. I can take the expression for B and then substitute it on there. And so here is what I end up getting, okay? So minus 0.15 alpha CDI minus 40 square times 0.15 J. That's what I have for the acceleration of B. Okay, so this is equal to, I'm going to start a huge bracket here, acceleration of A, which is 80 square times 0.1 I. Okay, and then 0.1 alpha OA J, okay, minus 40 square times minus 0.2 I plus 0.15 J, close brackets. And then you know the rest of the story, take the I terms and take the J terms, okay, and then start equating them to each other, okay. And then here if I do that, I get minus 0.15 alpha CD, okay. This is going to be equal to 80 square times 0.1 in the I direction, and then I'm going to have minus 40 square times minus 0.2, so there's going to be plus 40 square times 0.2, okay. So that's going to end up being alpha CD right down here, okay. That's the situation that I have. All right, there was probably, I just want to make sure that this 80 square is positive or negative, so let me just go back and look at it very quickly, okay, because my answers seem to be a little off. So I'm going to look at this 80 square here. Yes, I made a mistake here. All right, I'm happy that I caught it. So that's minus 0.80, so this is negative, okay, so that has to be negative. Thank you for letting me know. I'm just patting myself on my back. All right, so this is going to be negative, okay, so which tells me that this creature is also going to have a negative sign, which means that this is going to have a negative sign, okay. Then I'm going to do the same thing in the J direction. The J direction, everything seems to be hunky-dory. All right, so this is going to be minus 40 square times 0.15, and this is going to be 0.1 alpha OA in the J direction, and minus 40 times 0.15, so that's minus 40 square times 0.15. And you obviously see that I can solve for alpha CD, and then I can solve for alpha OA. What do you see for alpha OA? I end up getting to be 0, okay. So if I solve, alpha OA will end up being 0 radians per second square, and if I solve for alpha CD, I end up getting a very large value, but it's positive because of the fact that of this minus 0.15. So this is going to be 2133.3 radians per second square, okay. So which tells me that alpha OA at that instant in time is 0, and alpha CD at that instant in time is 2133.3 K radians per second square, okay. So this is the end of the problem, and if necessary, I mean, one part of the problem that I thought I would have done, but if not needed, I mean, I can just point this out to you, okay. So after all this calculation has been done, you know, then they will ask you, okay, hey, can you calculate the acceleration of point D? Okay, how to find the acceleration of point D? And I'm just going to write down the equation. So to find acceleration of point D, okay, I can see the D is a point on C, so use the bar CD so that velocity of D slash C relative is 0, acceleration of D slash C relative is also 0, okay. Then the acceleration of C is 0 because it's a fixed point, okay. And then CD, we have the angular acceleration and so on. Alpha CD was calculated as 2133.3 k radians per second square. Omega CD, if you remember it from before, was probably the same as omega AB, 40 radians per second, and then the position vector from D to C, that is sitting at the point C and then looking at the point D. This is going to be 0.15 plus 0.075. That's going to be 0.225 J, so many meters. Okay, and then if you do the substitution, acceleration of D, acceleration of C, alpha CD, D slash C, omega square CD, D slash C, then D slash C relative, and then lastly 2 times omega CD crossed with D slash C relative. Get rid of many terms. This is gone, this is gone, this is gone. Do the substitutions. Okay, substitute for alpha CD right down here, substitute for omega CD, and then all of these creatures as well. Okay, after all the substitutions have been done, I will end up getting, this is just a quick short idea in this problem, extra term in this problem. So minus 480I minus 360J meters per second square. Okay, so that was what I wanted to add on to the end of the problem. Okay, now very quick recap of what we have done. Okay, and I'll just leave it at that. So we started off with this following figure, where at that instant in time, okay, this is the bar CD is vertical and then the bar OA is horizontal, and I was asked to perform an Icr analysis to find the angular velocities, which means that I'm not going to use the vector equations for velocity analysis. That's exactly what I've done. Took the bar CD, figured out that, okay, hey, if I assume some rotational direction for a CD, then velocity of B is going to be pointing to the left or the right, but I know that it's horizontal for sure. Then I go to the bar OA, I know that the velocity of A is vertical for sure. It could be up or down, I don't know that. Then I go to the bar AB and then I figure out, okay, hey, I know the direction of VB, I know the direction of VA. I know angular velocity of AB is given to me. I can use the ICR. ICR, or instantaneous center of rotation, lies along a line that is perpendicular to the velocity of any point on the rigid body. So I draw a line perpendicular to VA, I draw a line perpendicular to VB. The intersection of those two lines is going to be the ICR for the bar AB. Okay, and using all the information that we had, we combined them all together in this particular page here, and we were able to figure out that, hey, the directions we assumed for VA and VB were correct based on the ICR location and based on the direction of omega AB. And since the direction of VB and VA were correct, the direction of omega CD and omega OA was also correct, as we assumed it to be counterclockwise. Okay, I'm sorry, I don't know what that is, but that's not something that I wanted anyways. It doesn't let me do it. Alright, fine. That was scary. Alright, then after that, you find the ICR. You see, we did not use any vector equations here at all. That is something that I want to let you know. That is what happens when you use the ICR. You don't need the vector stuff. Okay, this is just common sense or intuition in a certain way. Then I do the acceleration analysis the usual way. Collect the acceleration of B, relate that to C. Acceleration of A, relate that to O. Acceleration of B, relate that to A. And then combine all the terms, and I hope that everything works out. Okay, and it did work out. There was one scary moment where I forgot a negative sign, but thanks to my silent person on the back, I was able to figure it out. All right, so this is an excellent problem, and then we also found the acceleration of point D at the tip of the bar CD, okay, using whatever information we had already calculated. All right, thank you for your patience. I hope you have a fantastic day. Take care of yourselves. Bye-bye.